Here's some practice multiple choice questions on titrations. In the first, it says methyl orange is used as an indicator in a titration. What is the pH of the solution when the indicator turns orange at the equivalence point? So methyl orange will be red in an acid, yellow in the base, and right in the middle is its transitional color. So this should transition when the pH equals the pKa of the acid. So the Ka of methyl orange would be like 1 times 10 to the negative 4.2. And so all these indicators are just weak acids and weak bases. And if I take the opposite log of the Ka, it'll tell me the pH range, or I should see the color change. Because this changes color still in a slightly acidic pH range, it would maybe be a good indicator for a stronger acid and weaker base titration. Question 2, which of the following is not true of the titration curve? So the two most important points on a titration curve are probably points A and C. So the first statement says the resulting solution will be a buffer at point A. And that is true. Anywhere in this region where the pH is changing slightly, even though I'm adding strong base, means that the solution produced is a buffer. On the second statement, approximately 25 milliliters of sodium hydroxide are added to reach the equivalence point. Yes. So the equivalence point is halfway in the middle of that big jump in pH. If you follow that equivalence point down, it'll tell you the volume needed to reach the equivalence point. And so, yeah, it's right at 25 milliliters. Now, A then is supposed to represent the halfway point, halfway to the equivalence point. So, yeah, like around 12-ish, 12 and a half milliliters. And what's important about point A is that not only do we have a buffer, but we're going to have the special buffer solution that has a 1-to-1 ratio of acid and base. This is the titration of a weak acid and a strong base. Yeah, because if I take the equivalence point and follow it across, it'll tell me the pH. And so, yeah, with the pH still being slightly basic, then it must mean that the base was stronger and dissociated more fully than the weak acid, that even though at the equivalence point my moles of acid and base equal the stoichiometric ratio, because of the nature of the particle, they might not dissociate to the same extent and form the same amount of hydrogen or hydroxide. So equal moles doesn't always mean totally neutral. So not true is point E. E is not the equivalence point. It's just some point after the equivalence point where I've gone too far and in this case added too much base. Question 3 is some stoichiometry. We could have done this earlier when we did just stoichiometry calculations with a titration. I want to know what volume of 0.2 molar sodium hydroxide must be added to 50 milliliters of hydrochloric acid to reach the equivalence point. Titration calculations really are just stoichiometry, solution stoichiometry. There's one solution that I can use to find moles. So this time I know it's 50 milliliters of a 0.1 molar HCl solution. So I know I can get moles of hydrochloric acid. Being at the equivalence point means that I'm at the stoichiometric ratio from the balanced equation. So I did just check the ratio in case I wasn't sure, but this one is definitely a 1-to-1 ratio. Now obviously they don't have to be. If I had an acid with 2 hydrogen or a base with 2 hydroxide, I might not have a 1-to-1 ratio. Okay, so now once I get moles of one solution, I can use the ratio in the balanced equation to get moles of the other. So in this case, the beauty of the whole calculation is right in here, where if I do have a 1-to-1 ratio, then I know moles of the known solution equals moles of the unknown, which in this case is the sodium hydroxide. Now once I know moles of the unknown solution, I could do this, or they're asking what volume of 0.2 molar sodium hydroxide is needed, which if I know moles and I know molarity, I can solve for volume. If I knew moles, I could transfer that to grams. Maybe if it was an unknown base, I could find its molar mass. It's all kinds of things we can do as long as we know moles of the unknown solution. So here would be 25 milliliters if I solve for volume. Question 4, I like this one. A solution of a weak monoprotic acid, which just means one hydrogen, is titrated with a solution of a strong base. So I just called this random acid HA. They don't really tell me its identity. Strong base, KOH. Consider the points labeled A through E on the titration curve that is shown below. At what point are the concentrations of the weak acid and conjugate base approximately equal? That is your halfway point. The two most important points on the titration curve are the equivalence point and the halfway point. And so I just made up some numbers to show what happens at the halfway point. So this titration is starting off with an acid. The pH is like 3-ish, and I'm adding base. The pH is increasing. So let's just pretend, I just made up numbers. Let's pretend that I start with 1 molar acid. Well, at the halfway point, or the half equivalence point, we've got half as much of the base. So if I started with 1 mole of acid, I've added 0.5 moles of base. That's what it means to be at the halfway point, or the half equivalence point. I've got half as many moles of base. Now initially my two products are 0, and eventually I don't care about the water anyways. What happens as I fill out the ice table? Well, that strong base is my limiting reactant, so eventually that one is out and down to 0. But then do you see what happens as a result of the shift? The 1 molar weak acid is going to go down to 0.5 molar, and the conjugate base is going to go from 0 up to 0.5. So not only do I have a buffer, but I have the 1-to-1 ratio buffer, where if I use the buffer equation, Henderson-Hasselbalch, pH is pKa, or opposite log of the Ka, plus the log of this ratio, conjugate base over weak acid. Want this magical buffer, you end up with a 1-to-1 ratio. So when this is 1, the log of 1 is 0, and the pH equals the pKa. So if I follow this across, my pH is maybe, I don't know, like somewhere between 5 and 6, which means then that I could use that to identify the acid. I could determine its Ka value and then maybe look it up on a list of known weak acids. At point B, the halfway point, is where we end up with the 1-to-1 ratio of acid and conjugate base. Question 5, at what point is the pH closest to that of the strong base being added? And that would really be like up at point E, where if I were working this as an ice table, at this point when I've gone beyond the equivalence point, I've got excess strong base. And so if I have excess strong base, the pH is really just dependent on the amount of excess base in the solution. Strong base. Number 6. At what point are the moles of added strong base equal to the moles of weak acid? That is my equivalence point. I've got equal moles of acid and base, which then kind of shows the difference between the equivalence point and the halfway point. If I just made up random numbers here, that if I started with 1 mole of weak acid per liter, and once I get to the point where I've added 1 mole of base, that's the equivalence point. The The halfway point is when I added half as much base. Now, what happens then when you're at the equivalence point in the titration of a weak acid or weak base is that my two reactants are both gone. They're down to 0. And really all you have left is the conjugate base, which again is another reason why it's not neutral. Yeah, I'm going to form some water, but then the other particle is slightly basic. So my pH at the equivalence point with a weak acid and strong base should still be a little bit basic, which this one is. All right, another great question here. Check this out. Number 7. A 50 milliliter sample of a weak acid, called HA, of unknown molarity is titrated. Fantastic. And the pH of the resulting solution is measured with the pH meter and graphed as a function of the volume of 0.1 molar potassium hydroxide added. The student carries out the same titration but uses an indicator instead of a pH meter. Fine. If the indicator changes colors slightly past the equivalence point, so maybe they used the wrong indicator and that it turned colors a little bit too late in the titration, which means then that if I went past the equivalence point, too much base has been added. Oh boy. What will the student obtain for the calculated concentration of the acid? All right, well, let's see what's happening here. So if I have potassium hydroxide, 0.1 molar, and if I look on my graph, the equivalence point is supposed to be at 100 milliliters. So obviously then going past the equivalence point is going to mean that I've added more than 100 milliliters, and I'm up at like maybe point D or maybe E even. Well, at the equivalence point then, I'm supposed to have 0.01 moles of KOH. If I take that 100 milliliters, it's a 0.1 molar solution, I cross multiply, there's supposed to be 0.01 moles of KOH, which then, if I just have one hydrogen and one hydroxide, I know that they would have reacted at a 1-to-1 ratio. And now I could have written the balanced equation like HA plus KOH, but if everything's a +1 -1, I would have ended up with Ka, whatever A is, the conjugate base, and water, hydrogen hydroxide. Now obviously the potassium ion would just be a spectator, but it is 1-to-1 ratios, so that then the moles of base should equal moles of acid, and as long as I know the volume of acid used, I could figure out the molarity. 0.01 moles of acid divided by my volume in liters. Okay, so right there, that gives me a 50-50 shot of getting this multiple choice question correct. That the acid should have been 0.2 molar. So it's not the last two, right? It's supposed to be 0.2 molar. Well, now let's just look at what would happen if I went beyond the equivalence point. So instead of this being 100 milliliters of base, what if this number here is too high? I don't know, what if it's like 120 or 150 milliliters? Well, let's carry that error through. So I'm going to cross multiply, which then means that this moles is going to be too high. It'll be a little bit more than 0.01. It looks as though I have too much base. Well, what do I do with that moles then? I put it right here, because then moles of base equals moles of acid if it's a 1-to-1 ratio. So now my moles of acid is too high, which then being in the numerator is gonna make my calculated molarity a little bit too high. It's gonna seem as though there was more acid, that I needed more base to hit the equivalence point, which really isn't the case. I over titrated. I missed the equivalence point. So slightly greater than 0.2 would be my calculated molarity. What a loaded question. I have to understand the calculation to figure out, okay, what is the expected concentration of the acid? And then I have to kind of understand how this graph works and what it would mean to go beyond the equivalence point. Where's that error going to follow through in my calculations? Such a great question. I can't even handle it. Point A then, in question 8, it says, what particle is present in the greatest concentration in this region? Okay, so point A, point B, anywhere in that relatively flat buffer zone is going to give me a solution that's a buffer. And if I wanted to calculate the pH, I would be using the buffer equation. Okay, so if I know that the halfway point, which is point B, the half equivalence, so if the equivalence point is at 100 milliliters, the halfway point is at 50, that's when I have a 1-to-1 ratio of weak acid to conjugate base. Well, if I'm at point A then, the pH is a little bit lower, right? The pH is a little bit less than it is at point B, which then means obviously I don't have a 1-to-1 ratio. It must be a little bit more acidic. So it's a little bit heavier on the original weak acid. Isn't that kind of cool? That's a cute little question. Just understanding what's happening as I titrate. So again, I'm probably starting with weak acid. It's the same graph as in number 7. And so as I start to titrate, I'm forming a buffer. Anywhere below point B, I'm heavier on the acid in the buffer. At point B, they're equal concentrations. And then as I increase above 50 milliliters, now I'm going to be a little bit heavier on the conjugate base. Awesome. What a great set of questions. I'm obsessed with those two. And then here are the last two. Question 9. Here's that halfway point again. An unknown acid is dissolved in 25 milliliters of water and titrated with 0.1 molar sodium hydroxide. Which of the following could be the unknown acid? All right, so the two most important points on a titration curve are the equivalence point and the halfway point. The equivalence point is halfway up my big jump in pH. All right, so it looks like that's going to be around 25 milliliters. So my halfway point is going to be around like 12 and a half or so, halfway to the equivalence point. Okay, so if I take that halfway point and follow it across, I'll get the pH. So I'm looking for like maybe a pH a little bit less than 4. And so I just kind of estimated I'm probably about 4, which then that is the pKa. Because I know that at the halfway point, I've got the 1-to-1 ratio buffer. So the pH equals the pKa. So just by inspection, I'm looking for a pKa of about 4, which then would mean that the Ka is approximately 10 to the negative 4th. Well, here the closest is probably that glycolic acid, where the pKa is about 3.8. If I were asked for the Ka, I would say it's about 10 to the negative 3.8. And then finally, question 10 is a diprotic acid. So diprotic just means there's 2 hydrogen. You could have a triprotic acid with 3 hydrogen. And in your titration curve, you'll just see multiple equivalence points. So here at the first big jump in pH, the first equivalence point is where you lose the first hydrogen. So it'll be the H2CO3 giving off its first hydrogen, and the negative anion formed would then be the bicarbonate or hydrogen carbonate ion. Now up at the second equivalence point, that bicarbonate ion would lose its second hydrogen, and then the anion would be the carbonate -2 ion. We won't worry about any kind of calculations with these polyprotic acids. We just have to kind of understand that each hydrogen comes off one at a time, and I'll see multiple equivalence points on a titration curve.